Hey kids, time to do double integrals, but this time in polar coordinates. Brr, polar, pretty cold, right? So remember, one of the previous things that we've been doing is using the power of reversing the order of integration in order to help us evaluate an integral, right? Not everything can we integrate. Unlike differentiation, I can give you an integral and there's just nothing I can do or nothing I know how to do. So switching, sometimes I tell you to switch the order of integration, but other times you're supposed to realize, hey, I can't integrate this dx. But if I switch the limits, if I switch the order of integration and then switch my limits of integration, maybe I can integrate it dy and then dx. So we're just going to give you more and more techniques to be able to integrate impossible integrands. So another strategy is to transform into polar. A clue, now again, just like with the reversing the order, sometimes I will just straight up tell you to do polars, but a clue that you might want to do polars to transform, so you were in rectangular, is if you have any circular relationships. And here's what I mean. Well, first, think about why that might be so. From pre-cal and then again in calculus when you did polars, you recalled how to transform from rectangular to polar, right? I can take a rectangular x, that is the same as r cosine theta. A rectangular y, that is the same as r sine theta. And of course, my circle centered at the origin, x squared plus y squared is equal to r squared. Theta is just the inverse tangent of y over x. Right? So I have some formulas to go back and forth between rectangular and polar. So before we get into a problem, let's look at some pictures. Now, this is a bunch of words, blah, 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 blah. But what I want you to think about is instead of our domain region being down on the xy plane, our domain region is going to be down on the polar plane. Right? So I'm going to, instead of looking at the XY plane, I'm going to legally transform it into a different looking plane. And then I'm still going to, right, look at that area or a surface above it and the volume. So here's a picture where, remembering that if I'm in polars, I start at the pole, I give a certain radius, I radiate out, and then rotate up. Right? And there's my theta. Or I radiate out a certain radius and rotate further. And there's my beta, right? My two radii. And then you can think of, well, in between, in that sector, there is a change in theta that happened, as well as a change in r, right? And then what we're gonna do is just imagine taking the limit, blah, 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 of all that stuff. Remembering also you had a formula that area is equal to 1/2 r squared theta. And I'm going to write it like this. Right? So again, think about what you're doing with Riemann sums. You're adding up a bunch of, this is going to be our domain region. We're adding up a bunch of things inside of here, right? Picking a point. And we're going to have our change in theta and our change in r. We're going to take those, the limit as they go to, right, as they get very, very large. So we're going to, instead of having triangle theta and triangle r, it's going to turn into d theta and dr. And we're going to have a whole bunch of, take those to infinity, right? So here's what that looks like after we get done with Riemann and make it Leibniz-like. If you have a simple polar region, right? So you've got a whole bunch, things nicely laying down there on the polar region. And if your function is a polar function in terms of two variables, r and theta, then the double integral over that region of that two variable function with the delta area. But look what delta area has turned into. The change in the area, right? This is the height times the change in area. Look at what the change of area has turned into. not just dr d theta, right? There is an extra r from the area. So it's r dr d theta. That is my dA. So when you transform from into polars, but this delta area was dx dy or dy dx, when you want to transform everybody into polars, you have to transform that into r dr d theta, and we are not going to, because of that extra r, we are not going to mess with the order of integration. It is always going to be like this. And I kind of think of this as this extra r as my price. The price to pay for transforming dA into polars is this extra r. And then I have dr and d theta. Okay, but don't forget that price to pay. Oftentimes, if you drop that extra r that's in there, your integration isn't possible still, right? Or is incredibly nastier. So please don't forget the price to pay for going from rectangular to polars. Of course, the other thing I have to do is make sure that I've got my, since theta is on the outside, here is my smaller theta and my larger theta. And then here are my equations, R1 in terms of theta, R2 in terms of theta. And then, of course, my function is in terms of R and theta. If it is not, if you start up here, sometimes what I'm going to do is give you a function in terms of x and y. Then you also, using the formulas that I gave you before, have to transform this into r comma theta. Okay, so let's try some. Let's try one. Oh, I forgot that I highlighted some things, like don't forget with some boxes. Your function needs to be in terms of r comma theta. If it's not, you have to transform it. You have your delta r really is r dr. And then you have your inside limits of integration are r functions, r in terms of theta. Then you have your d theta on the outside. So you have your limits, your outside limits of integration are theta values. So here we go. Copy down those two equations. Notice they're already in terms of r, so there's no need to transform anything. But I want you to look at this word, area. Area. Now, I don't know if we've quite made this distinction before, but when we've been doing double integrals before, we've conceptually or visually, or however you want to think about it, talked about, right, this is area times that height, because this is z equals a function in terms of xy, right? So we're talking about a volume between a surface in the z plane and an area on the xy, right? The domain area on the xy. And we're taking delta area, multiplying it times the height, adding them all up, and we're getting volume. Well, what happens here? What if I just have a 1 dA? What does that mean? You still have area, but your height, right? What are you multiplying the area by? Just a 1, right? So if you end up with a double integral that is 1 times the area, isn't this actually just an area? A way to get the area with the double integral? Kind of crazy, right? So notice that this problem is asking me for area. So I drew the regions. Yes, I do kind of sort of have to know, not completely, but this shouldn't be too bad, right? 2 sine theta. I have a positive here, so in the y direction, I'm longer, and you can just plug in values, right? Sine of pi over 2, is 1 times 2 is 2 plus 3 is 5. R is equal to 2. Hopefully that's not too bad. I have a circle centered at the pole with a radius of 2. So I want the area, don't want volume. So my integral, my double integral, needs those points of intersection, which I get from setting one equation equal to the other, just like I do any intersection. So what do I have? 2 sine theta is equal to 2/3. I'm silly. -1. So sine theta is equal to -1/2. I'm in quadrant 4 and in quadrant 3. So I know I had this is a pi over 6 issue, right? Theta that has a either positive or -1/2 is a pi over 6 issue, and I just have to figure out where I am in quadrant 4. Sine would be negative, and here sine would be negative in quadrant 3. So area, see how this is area because the integrand is just a 1? So this is the area. I'm not building up from this at all. I'm just looking down on this. But notice my dA, when I transformed into polar, my dA was that extra r dr. I still have the integrand of 1. But dA, pay the price. Not just, I can't take dA and change it into dx, dy, dx, or dr d theta. I need to, in order to transform my space legally, I need that extra r. Now, in Calc 1, or Calc 2, I guess, BC, we did areas of polar curves, but this one would be heinous. This would be so, it's not just like top minus bottom, right? Because like this that isn't just the circle right there. I mean, it would be harrowing. But with double integrals, I can do this. So notice all I am just integrating on the inside first. So I'm just integrating r, and I get r squared over 2. Integrating at r equals 2 and r equals 3 plus 2 sine theta. So I have to do a little bit of algebra. I'll keep the 1/2 on the outside, and then I've got to square 3 plus 2 sine theta, and I got to square 2. So after I do all of that algebra and combine, this is the expression I get. Now, I'm down to Calc 1 mostly, right? This is just integration of 3 terms, all d theta, and these are theta values. But the only thing I didn't do to you in BC was this identity. And I gave you this identity before, and I said we use it a lot in multivariable. Right, this one is sine squared right? So I'm going to replace that. I'm not doing any calculus yet. Notice this 1/2 canceled out with this 2, right? So that canceled out, and I was just left with 1 minus cosine 2 theta. This 1 I turned into 2 over 2 to combine with the 5 over 2, so that's where the 7 over 2 came from. And then I have my minus cosine 2 theta right there. And now I'm just going to integrate 1, 2, 3. 7/2 theta minus 6 cosine theta. Don't forget the chain rule here. The antiderivative of negative cosine is negative sine. Right, the anti-chain rule. So you have to divide by 2. And I'm going to plug in theta equals negative pi over 6 and 7 pi over 6. And I hope you can just trust me that those are the values that I got. And yes, I used a calculator certainly at the end. All right. So again, important to realize there that was just an area problem, a polar region, but kind of a complicated polar region. Now look at this problem. This problem I've already got all in polars for you. So what am I doing though? Am I finding volume or area? What do you think? Yeah, as long as you recognize that this is your dA, this used to be dA, right? So your integrand is really a 1. But these are R values and theta values. And just like before, I should draw this. Let's say, what is my region? Well, let's see. I'm going from theta equals pi over 2 to pi. Oh, it's terrible. So bad. Sweeping out, right? Because polars are like that. On what circles, right? R equals 0, well, that's right there. 2 sine theta is that whole circle. So R equals 2 sine theta is a circle with a radius of 2, but not around the pole, starting at the pole. And then I'm going from pi over 2 to pi, right? I really should have drawn the circle first. So this is what I'm after. I'm after this area here. Oh, I think I know what the answer is. Do you? Let's pretend I don't. This, once again, I'm going to do the inside part. And I have 1/2 r squared from r equals 0 to r equals 2 sine theta. So the 0 is nice, right? Because I'm just going to get 1/2 4 sine squared theta, which of course is just 2 sine squared theta. But now I'm going to do the outside integral. I've got to use my identity again. So I'm going to have 1/2, which is going to cancel with that 2. And I'm just going to have 1 minus cosine 2 theta d theta. Integrate that. And I have theta minus 1/2 sine 2 theta. Evaluated at pi over 2 and pi. So I have pi minus 1/2 sine of pi, 0, minus pi over 2 minus 1/2 sine of 2 times pi over 2, but that's just pi, which is 0. And I have pi minus pi over 2, which is, shocker of all shocks, pi over 2. Hopefully that didn't shock you too much. Oh, sorry, I did say the radius was 2. I meant 1. Has a height of 2, right? All right, so let's do another one. Now notice this one. Firstly, what's different here? is that your integrand is in terms of x and y, and you have an integrand that is not just 1. The region that they're giving me to integrate is the domain, is the upper half plane bounded by circles. Clue. Should I do polar? So if I'm going to do polar, I have to transform the integrand, and I have to transform dA. And remember to pay the price. Can't just go directly to dr d theta. You have to have your r dr d theta. So I also have to transform everybody. I've got to transform this equation and transform this equation. But look at those. They're circles. Circles. This is just r squared is equal to 1, and this is just r squared is equal to what? Not 4, right? Well, r squared is equal to 4, sorry, but my radius is equal to 2, right? So what does that mean? Let's draw a little picture first. So upper half plane, so that's in quadrants 1 and 2, bounded by the circles where I have a radius of 1 and I have a radius of 2. So think about theta. What is my theta going to do? How are you going to radiate around? Right? For either one of these. Isn't it just 0 to what? Yeah. There's my thetas. And then how about my r's? What are my r's going to be? Well, if r squared is equal to 1, the smaller circle is r equals 1. And if r squared is equal to 4, what is r equal to? 2. So I've taken care of my region, right? This is my region down in the domain. This is my domain region, right? I've taken care of the angle that it sweeps through, and I've taken care of the curves that describe it, the polar curves that describe it. I've taken care of transforming dA. Check, check, check. Who haven't I done yet? Right, I haven't done the original. So what is this? This is where you need those equations. So this is 3x plus 4y squared. In polars, transform x, transform y. So when I'm done with that, clean that up a little bit. I've got 3r cosine theta plus 4r squared sine squared what do you have to do? You're not going to end up with just an r, are you? Here's your price. Your price is you've got to distribute this through. So my integrand, where I am doing r is equal to 1 to r equals 2, is actually 3r squared cosine theta plus 4r cubed sine squared theta. But when you integrate that with respect to r, right, who's a constant? When you integrate with respect to r, cosine theta and sine squared theta are just constants, right? So I end up with 3r cubed over 3. So that's just going to be r cubed cosine theta plus r to the 4th over 4. Oh, isn't that nice? Evaluated at 1 and 2. So I ended up with 8 cosine theta plus 16 sine theta minus the quantity cosine theta plus sine theta. So I ended up in toto with 7 cosine thetas and 15 sine squared thetas. But what do I have to do with that? The double integral, right? But now I'm going to integrate d theta from 0 to pi over 2. I'm sorry, 0 to pi. Right? And once again, look what you have to do here. So you're going to have to replace that with 1/2 times the quantity 1 minus cosine 2 theta. So you're going to end up with a 15 over 2, aren't you? So when I ended up integrating the cosine, of course, I got negative. I'm sorry, positive. Sorry, I was like, my notes say negative there. 7 sine theta plus 15 over 2. And remember, that's 1 minus that cosine 2 theta. So I ended up with, after integrating, theta minus cosine 2 theta over 2. And this was all of this I was integrating from 0 to pi. And when I was all done, I got 15 pi over 2. Woohoo! Let's do another one. Find the volume of a solid. So my integrand is not going to be just 1. It's going to have a function. Notice I'm in all x's and y's above the xy plane. I am dealing, they told me, a paraboloid. Clue. Kind of sort of circular, right? Do you see my r squared in there? So maybe I can integrate this dx or dy or dy dx, but look what's going to happen here. If I put this into polar form, z is equal to, right, this is just minus 2x minus 2, and then x squared plus y squared, right? So 18 minus 2r squared. And then z equals 0 is the xy plane, right? I'm going to go from 0 to 2 pi, sweeps through the entire paraboloid, right? So if you need a refresher, right, you graphed these at the beginning, didn't we? So I have a paraboloid. Oh, that's so bad. Gee, Merry Christmas. Terrible. But down on the xy plane, I want to get the whole 0 to 2 pi. My boundary is the intersection of the top and bottom. So I'm solved, right? I'm setting the planes equal to, right? Z is equal to 0, and Z is equal to 18 minus 2r squared equal to one another, and solving for r. And then I can set up my double integral. So here is my transformed polar integrand. Here is my pay the price transform dA. Here are the r values I got from subtracting 18 divided by -2 and getting 9. So r is equal plus or minus 2. Remember, when you're dealing with polars, I only need that positive value for the radius. And then these are my theta values. That's a nice, now don't forget you have to distribute your r. So you have 18r minus 2r cubed. But what's awesome about this one that wasn't true for the other ones is I want you to notice what the bounds are on there, on both integrals. On both integrals, I've got constants. Do you remember something that you're able to do then? Do you remember that guy? Right? Because these are all constants, instead of doing my iterated integrals, I can just do this, right? Where I integrate from 0 to 2 pi d theta, and then integrate from 0 to 3 dr, and do those separate integrals. And notice what happens here, right? There's a 1. So the first one ends up being just theta from 0 to 2 pi. So hopefully you can see that that's just going to be 2 pi times this integral, which is going to be what? 9r squared minus r to the 4th over 2 from 0 to 3. And when you do that, and you're going to get right, you're going to integrate that. Of course, when you plug in 0, you're going to get nothing. So you're going to get 9 times 9, which is 81, minus 64 over 2. Oops, sorry, 3 to the 4th is not 64, silly. 81 over 2. And then you're going to multiply by 2 pi, and you're going to get 81 pi. Woohoo!